Комментарий к Игнасу. По-русски подводные комнаты называются граблями. Я опять перейду на английский сейчас. Значит, мы будем говорить о segment routing с MPLS Data Plane. В принципе, топик достаточно близкий к моему сердцу, потому что занимаюсь 10 лет уже. В принципе, полностью дизайн и построил имплементацию, то есть знаю достаточно много. So I would like to discuss with you what is segment routing, how it's signaled, why are we doing segment routing, and probably most important topic outside of segment routing itself, how it's being used in SDN ecosystem, how we do learn about the network, how do we program the network, and some use cases with it. So some history. When you hear Cisco saying we invented segment routing, they didn't. In 2004, in Redback networks, hopefully there are still some people using us, we published a draft that describes what segment routing is. It's really domain white labels. We use LDP as control plane. In today's incarnation of segment routing, we use IGPs directly to signal labels. However, this is where it started. So in 2012, Cisco filed about 40 patents on it and started to promote SR, also working with IETF, so with all the people around to get stuff done. In 2014, IETF formed a new working group called Spring and started working on several segment routing documents, as well as ISIS, OSPF, BGP, PSEP extensions have been developed, and now in final stages. So we are going to see RFCs probably within 2-3 months from now. So what is segment routing? It's really an abstract routing model, very similar to that of idea of MPLS itself. You have a piece of metadata attached to a packet, you look it up, you do something with it. The idea behind segment routing, you only look up your packet once. So it's very similar, again, to our MPLS network, when only ingress router looks up the IP destination address, assign labels to it, and the rest of the network just using labels to switch the traffic. So in SR case, only ingress node understands full context and defines full path throughout the network, either strict, hop by hop, or loose, where IGP is still used to compute shortest path. The difference with vanilla MPLS, we decoupled forwarding from the metadata itself. So in LDP or CPT networks, label only means forwarding instruction. In segment routing, value of the label could be used for any function. Obviously, forwarding features primarily function. However, it could be copy me, send me to some other place, do something with me. It's just piece of metadata attached to a packet. Very important, and MPLS is really very well thought architecture. Even so, today you hear that SD1 is going to replace it. It's not. You could look up one label in context of another one, which gives you the ability to build really strong, logical constructions that are not atomic in a way. You could do recursive lookups and build very complicated way of doing things. For example, service chaining. So how do we start? When we configure a device to support segment routing, device itself will advertise, hey, I support segment routing, done through capability advertisement in either OSPF or SS. Together with the capability, device will also advertise the SRGB, the block of labels assigned to segment routing. It will also advertise SRLB. It's a local block of labels that are defined locally to particular functions that are programmed from outside. For example, SDN controller. So encoding is very straightforward. Range of labels, and labels up till we define the label itself. we are going to look into base segment routing seed types. There are more use cases and some more, but this is the foundation. Prefix seed. It's a seed or a label, in this case, assigned to a particular prefix. Has to be within SRGB. So when the router receives a label and looks it up, it knows it's a segment routing label. It's not BGP, it's not RSVP, it's a segment routing. SRGBs are advertised by an IGP, so like in previous slide. Prefix seed can be configured as an absolute label or as an index. Why? When we started segment routing, no OS, no vendor could support configurable label ranges. So every code base has H file that says, my labels 10 to 20 are RSVP, my labels 50 to 100 are BGP labels. So Juniper couldn't interrupt with Ericsson, Ericsson couldn't interrupt with Cisco. To solve this problem, we decided to use index. So in this case, I could use any label range, and I'll only advertise index to my peer knowing the index and knowing my label block advertised in the router advertisement. When sending traffic to me, can compute value that is within my SRGB. So this was major change to provide interoperability. By using indexes, any vendor can interrupt with any other vendor. Not seed. Not seed is a type of prefix seed that is used to identify a node. Think of your loopback. So it's a prefix seed where particular flag set to signal I'm the node ID. Think about router ID. Think about something that uniquely identifies a node. It must be unique within the network, because this is how we find a device. Adjacency seed has been designed to provide traffic engineering capabilities. So if you only use nodal seeds, your routing is going to look exactly like LDP. If I say I need to follow router 1, 2, 3, 4, 5, I'll use IGP to compute shortest path and just follow it. So what we achieved, we just replace LDP. In order to provide traffic engineering capabilities, we needed to be able to override shortest path decision and send traffic out an interface or adjacency that is not on the shortest path. So this is exactly how adjacency seed is used. Adjacency seed could be local to the device. So today, if you configure Cisco router with segment routing, it will automatically assign local adjacency seed to every interface configured for this particular IGP. It has some implications. We'll talk about this later. So encoding of prefix seed, straightforward. You've got seed or index. You receive it. You know how to map a label to a prefix. Nodal seed is a type of prefix seed, as we said. You see flags as defined, flag N defines the nodal seed. When it's set, our IGP knows it's a nodal seed. So when you do show LSDP for SS or SPF, you'll see that if nodal flag is set, it's a nodal seed. Adjacency seed, from advertisement perspective, looks very similar to nodal seed. However, it's always encoded absolute value. It cannot be indexed because it's local to the node that has assigned it. Binding seed is an interesting entity. Initially defined to attach an RSVPT LSP to segment routing node. Has a lot of RSVPT semantics, ERO, some other stuff, backup, primary, has been removed. However, we are bringing it back for two reasons. It's needed in a specifically to provide mapping server functionality. Mapping server is a device that connects LDP or RSVP domain to segment routing domains. So it's needed there. Another one very important reason is to be able to cross-connect different networks, to cross-connect networks that are at different layers, for example, optical network. And we'll talk about this use case. It's quite interesting. So binding seed is configured either locally or through any other protocol of your choice. So this is specific encoding to support optical domain capabilities. So it gives us ability to signal, hey, there's an optical link below with particular characteristics. If you want to use it, just set this binding seed at ingress router, and when it reaches the node that has both IP and optical capabilities, we will push it down to optical. Very, very useful when you're trying to engineer interlayer connectivity and traffic engineering. So some basics. In LDP, labels are assigned independently. So as we go throughout the network, we would assign just any label value available. In segment routing, we introduced new option called continue. What it means, we swap or replace same value by same value. So as you could see here, node Z, that is the destination, has assigned nodal label 20. And as we go throughout the network, we just change label 20 by label 20. Why is it important? Imagine labels would have been different. We would have had to build label stack assigned by every device, right? So it's getting quite large, and again, has a lot of implications. In this case, it's a single label, and it's enough to get to the destination. And forwarding behavior is same as LDP. We use OSPF or ISS computed path to get to the destination over shortest path. Adjacency seed, as name suggests, is assigned to an adjacency, or a link in this case. So as you could see, here it really identifies link between C and O. So when I get to node C, and I see label 9003, I'm not going to follow my IGP anymore. I'll be forced to push traffic down to node O. So I'm doing traffic engineering. From scale perspective, only node O node C has to instantiate it in forwarding. For the rest, it's just control plane information. It doesn't create really any state in the network. So how does traffic engineering in its extreme version works? Node A would instantiate full label stack, so in this case, 5 labels. And as we go through the network, we just pop labels. So very simple. Could be used for OEM, could be used for services where deterministic path is important. As an implication, it requires to push 5 labels. So it's kind of entirely different talk about how many labels are supported. If you take vanilla Broadcom using today, something like Trident 2+, it can give you 4 labels, including service labels. So if you are doing L3 VPN, you are left with 2 labels. You need 5 here. So what we can do is to compress. An intelligent algorithm should be able to figure out there are some pieces that could be instantiated as loose paths. So in this case, paths from A to C could be done as loose paths. So I only need to define A and C. I don't need to define B. Getting from O to Z, again, could be done loose because this is the shortest path. So in this case, rather than using 7 labels to traverse every node, I'm going to use only 3. So label 72 that identifies node C, label 9003 that is the adjacency seed pushing traffic to O, and Z. So it solves a lot of problems, but not always. So there's a whole different framework to alleviate these issues. Probably subject for next time presentation. All the drafts are now going through latest stages, going to become RFC within 3-4 months. So binding seed could help in this problem as well. Binding seed is an instruction to expand your initial label stack to a new one. So in this case, as you could see, rather than pushing 7 labels, we are pushing 3 because it's what's supported. And the last label, or one before service label, is a binding seed. So when we get to the device that is anchor or the initiator of binding seed, it replaces it with new label stack. So by segmenting your network into number of LSPs with binding seeds, you could actually segment it in a way that is supported by your hardware. Again, requires some intelligence in your computation logic, in your PC, requires a management session to the device to provision binding seed. So again, something to think about. So how do we make SR work across domains? BGP is our friend here. What we've done with BGP, we extended it to signal everything we've got in segment routing in IGP. So there are a number of extensions to BGP link state that takes all the labels, all the states available in single IGP domain, being translated into BGP attributes, and could be sent to another domain where it's instantiated in the new IGP again as full segment routing stack. Same could be done with data centers. In my previous life, we've done something like that in radio. So segment routing allows to build end-to-end networks and use BGP as glue between them, also providing some filtering, normalization, and so forth. So segment routing in SDN. And SDN is a very important point for segment routing to exist. Back in 2004, it was rejected for exactly the same reason. We don't need it. LDP is good enough. Why now it's the most popular technology in IP? SDN. So it was sold under focus of, look, you can use it in SDN, and it will solve all your issues. And it does solve a lot of issues. So why are we doing this? So first of all, in order to scale, we need to separate policy from reachability. That's why we are doing L3 VPNs, where our reachability is in the underlay in IGP, and our policies, which prefixes to export, to import, is in BGP. That's why L3 VPN scales so well. That's why I particularly dislike SRv6 ideas where services encoded in the reachability itself. But this is another discussion. Just to reiterate what Ignas said before, there is no way to build scalable network with fully centralized model. So segment routing provides us with the ability to have dynamic control plane and have centralized view on it. So it scales independently, and hence you can build large networks that are still flexible, can recover fast, and just working. Why are we using routing as database? Because in this case, routing is nothing else than database. Your LSDB is a database that is eventually consistent, available, and partitionable. It's a pretty good database. In doing this for 25 years, we figure out how to build routing, being consistent, being fast, and pretty much bug-free. So it's a good thing to have something done by routing protocol rather than magic SDN controller. So the motto here is logically centralized. So remember, centralized view of the network while physically distributed. So we still leave devices some intelligence. They can exchange it. They can recover themselves. They're doing it much faster than if they need to talk to centralized magic OpenFlow controller. Max. So how does the stuff work? In the past, when we built PC-like controllers, we would configure OSPF or SAS on the controller itself, and we would peer passively to learn prefixes. The problems with using IGPs are a lot of information is area-level specific. As you go into larger network, as you go into multi-area deployments, you need to build GRE tunnels. You need to somehow tunnel those information. So to alleviate a lot of these problems, we designed BGP-LS, BGP link state, de facto a transport to take LSDB of an IGP and send it somewhere else. On top of BGP-LS, we've also built segment routing extensions. So for particular reason here, we will take all the segment routing state and send it to the controller. So this is the MD cell present in OpenDaylight controller, but pretty much any other SDN controller of your choice would do exactly the same thing today, be in Cisco, be in Nokia, or be in Juniper. So when we receive all the information, we receive information about node links, so we have full networking graph. We also know all the labels assigned by segment routing. We also know all the attributes of these labels. So we can build full topology graph. At this point, we can expose it to external application that could compute a path following some business logic. For example, a path that is of particular latency, path that has a backup, path that is different than some other path. So anyway, it's really your business logic instantiation in forwarding. So we've learned all the topology. What's next? In most cases, this logic called PCE, path computation element. So it takes our networking graph, it applies some constraints, so again, being latency, protection, hop count, you name it. You should be familiar with this concept from RSVP days. So in this case, we also use PCEP, which is a protocol that is used between PCE, that is the controller, and PCC, that is the router itself, to communicate path that is computed. And looking into multi-layer models, Yang give us ability to model full networking stack with segment routing as an underlay, with, for example, L3 VPN as an overlay and instantiate it. This is working today if you use OpenDaylight. So some use cases. SDN orchestration. I'll be using OpenDaylight as an example, but again, if you are using something like Cisco or Carrier, you use Nokia or Juniper products, you see pretty much the same thing. So we assume controller knows all the topology. So it has full networking graph, meaning nodes, links, bandwidth, and delay in this case. So an application is asking for a path that has particular characteristic. So in this case, minimum bandwidth available should be 10 gig and max link delay 10 milliseconds. We take a look in our graph, we see that link BD is too short or too slow for us. We prune the link from the topology, and the only link available in this case is the link below, ACEF. The link is instantiated as stack of labels. So we're talking about MPLS here, right? Segment routing MPLS. We use PCEP to send this information to the ingress router. Ingress router creates forwarding entry, and next time a packet to the destination comes, it will be encapsulated in label stack CF and sent over. So see, it took 40 seconds to configure a new service. Before, it would probably take us 4 days to do this. Right? So it's really what SDN is in essence. Its ability to automate process and bring business logic close to networking. So another interesting case of having centralized view of the network. So in this case, as you could see, application is asking for 15 gig. So we've got no larger link than 10 gig from the ingress router. Practically, we should say, we don't have 15 gig of capacity, so there's nothing we can do for you. However, since we've got full view of the network, and we apply service not to the node anymore that has 10 gig link, but to the network itself as an entity, we know that if we load balance traffic between two links, we can actually provide 15 gig. So what we do here, our computation will tell us, look, if you use both links, you can actually send 15 gig and provide the service. So we are going to tell the router, if you load balance traffic across, you're actually allowed to do this. There's a concept in segment routing called bundling. In this case, you could say, if you look up this label, you load balance, you load share. So we are provisioning this kind of seed, two LSPs are established, and new service is available. So it provides you much better utilization on the same hardware, meaning really more money. Something known as machine learning, whatever you call it. De facto, what do you do with the information that comes to you as telemetry from your network? So worst case, you just keep it on a hard drive and throw it away. By using it actively, and that's why pretty much every major vendor is giving you telemetry today, you could actually fix your network automatically. So a very simple case. One of your nodes is telling you, look, I'm getting overloaded. Don't send traffic to me. So in this case, since we've got full topology, we can see that there's another link that has enough bandwidth. And the traffic could be moved to this link without any interruption. So what we're going to do here, compute new link, push it down, shut down old link, and move traffic to the new one. So we just fixed our network before it broke. And this could be done for many other different reasons. And those of you who have been to UNOC yesterday, so last presentation was from packet design, talking about machine learning. This is exactly how you instrument logic of machine learning into networking. So interworking with optical is important. Usually, optical people are very different than IP people. They don't necessarily like each other, and sometimes it takes weeks to get optical people to provision anything for IP people. In this case, by using binding seat and agreement with optical people, you can just ask them, you know what, give me your optical links and give me binding seat values I can use. I don't need you anymore, just provision the stuff. So in this case, you could go compute a IP MPLS path, but also include optical cross-connect into it in form of binding seat. So now suddenly, again, you can provision your service in minutes in cases where before it would take weeks, and also configure optical part, which is not really yours, but you're provided enough means to do so. So this is relatively new stuff, and actually I'm quite excited. This is stuff I'm working with Noash as well. If we look at majority of data centers today, they don't support MPLS, so Young is an exception. In most data centers today, we do IP routing. We use VXLAN for an overlay, and we use VXLAN source port for entropy. So, but what do we do if we want to provision end-to-end paths, and we use IP in the data center, SRMPLS in the WAN, and then again IP. And this is where MPLS and UDP comes into play. So there's an RFC 7510 that defines how we encode MPLS and UDP, and there is an IANA assigned port number that tells a device, hey, look, it's not only IP UDP, there's also MPLS inside. The idea here that we can program our cloud management, so OpenStack, VMware, whatever we use, to program complete paths end-to-end. So not only within data center, but also throughout DC gateway, to remote DC gateway, and to remote end. So for the first time, we can actually control how we leave data center and paths taken outside of data center. So how does it look? After we've imposed MPLS seed stack, we look who is the next router that's going to support segment routing, and we put its destination address, and we put UDP header on top. Very important, we've got UDP destination port that says, hey, there's MPLS below. So when you look me up, it's not just IP routing, you need to look MPLS. So while we are within data center, we are just doing routing. We are going towards the data center gateway. When we hit data center gateway, we know there's MPLS inside. We remove IP UDP. Suddenly, we look at segment routing that is full path throughout the network, traffic engineering, and all the usual traffic engineering techniques we could apply before, again, we had to interwork with one people that is usually another team. Now we are empowered to program full network. So more details here. Another interesting property of this solution, if there's part of the network that doesn't support SR-MPLS, we could always encapsulate it in IP UDP and traverse IP network before we hit another router that can do SR-MPLS. So this also gives interoperability. This also works with IPv4 and IPv6. It's just IP. Could be either version with UDP on top. So from my point of view, it's an almost perfect solution for data centers that don't do MPLS. And again, most don't. And I foresee future for this solution. So to finish, why people deploy segment routing today? It simplifies your network. It gives you programmability. As you've seen, it's reasonably easy to program. It's reasonably easy to take business intent and instantiate as networking. Those of you who try to operate LDP and RSVP know how complicated this is, especially when your RSVP network starts growing into thousands of tunnels. So SR removes the state completely. Fast recovery. SR, since it supports traffic engineering, gives you faster route that is topology independent. There's a variety of technologies that give you IP faster route. So LFA is most well known. However, they're all topology dependent. In rings, they don't work. In irregular topologies, they don't work. So-called topology independent LFA that's built on top of segment routing works in every topology. So your network is protected from any failure in any topology, and you know that it's going to be recovered below 50 milliseconds. The forwarding is really MPLS. So most of your hardware today can do it. Most of the hardware you are going to buy today, tomorrow, so Barefoot, Mellanox, Broadcom, Trident 3, Tomahawk 2 can do this, and can do this really well. So it gives you the ability to keep your costs relatively low because it's vanilla MPLS, so it doesn't have to be something expensive, complicated, while you can use all this great technology. Since we can use the SR values as metadata, it gives us ability to interact with other layers in the network. Could be lower layers, so optical network, could be higher layers, so segment routing could be used for service chaining, for firewalling, for anything you can imagine. You just need to say, hey, this is label 10, go firewall it. This is label 20, do something else with it. So it extends capabilities of what we can do today with AP. I've included all the information of different working groups in ATF. So most of drafts are in very, very solid state. Most of them will become RFCs this year. There are at least 4 to 5 implementations, including open source one. So FRR, that is the Better Quagga, has implemented SROSPF 2 months ago, contributed by Orange. So if you want to run it in open source, it's there. And most importantly, together with kind of the core work, the OSPF and IS work, we've built all the ecosystem needed for it, being BGP, being PCEP, being netconf. So it's all for you to use. Спасибо. Вопросы?
Мы ждем вопросов. Так. И, возможно, у нас будут вопросы из онлайн, как обычно. Микрофон есть где-нибудь поблизости? Ага, сейчас будет.
Спасибо большое еще раз за рассказ. Собственно говоря, это в некотором смысле продолжение беседы, которая началась у нас в понедельник, в общем-то, про SR и все остальное. Что меня больше всего смущает до сих пор в SR, это вопрос, то, что раньше у нас была децентрализация, и, в общем-то, связанная с этим надежность. В общем-то, мы строили изначально IP-сети под ядерную войну, у нас туда падает бомба, и все остальное продолжает работать. Сейчас же у нас будет контроллер, который достаточно сложный. Он не очень простой. Если кто-то лазил внутрь OpenDaylight, надеюсь, вы не сильно ужаснулись. Вот, там очень много разных палочек расставлено и прочих вещей. Что мы будем с этим делать, надежностью? Это раз. Два, многие вещи еще не решены. Мультикаст, который в сетях дата-центра, понятно, не везде нужен, а у операторов, в общем-то, очень много где нужен. Ну, в общем, много еще можно о чем посудить.
Я по очереди отвечу. Segment routing сам по себе в контроле не нуждается. Он fully distributed. То есть если у вас есть network, в котором есть ISPF или SAS, вам просто нужен код-бейс, который, кстати, работает с SR. Контроллер нужен для того, чтобы сконфигурировать что-то, что traffic engineered. То есть когда pass, он не shortest pass. Иначе segment routing работает. Ваш контроллер умирает, ваш segment routing все еще работает. То есть это строилось с идеей, что должно быть distributed is distributed. Второе, да.
Да, но другой вопрос, что если сравнивать с RSVP, например, то RSVP у нас все хосты знают по дороге, что у нас творится с зарезервированной полосой, собственно говоря, и они знают, когда она кончается. В сегмент раутинге это у нас отдано на откуп контроллера, который должен уже пересчитывать, перекидывать трафик и прочее, прочее.
Значит, мы всегда пытались бороться с количеством стейта в нетворке и, собственно, complexity. То есть в данном случае решение было принято убрать стейт из нетворка полностью и упростить его, потому что сегмент раутинг, как вы сказали, он не создает никакого стейта в нетворкинге. Он полностью stateless. Если вы работали с RSVP, то вы знаете, RSVP — это soft state protocol, который refreshes, который signal, все. То есть когда количество туннелей превышает 1000, то начинаются грабли, мягко выражаясь.
Мультикаст.
Значит, мультикаст. Значит, есть возможность строить мультикаст сегмент раутинг, где он используется как unicast туннель. Это, собственно, моя работа с Дэйвом Алланом. Есть драфт, который написан, который не любит ни Cisco, ни Juniper, но мы математически доказали, что он работает, и, в принципе, если он кому-то нравится, поддерживайте, и кто-то построит. В принципе, мультикаст BIR развивается. Мы увидим в этом году первые имплементации от Cisco, Nokia и Juniper. И BIR, в принципе, это отличная замена тому, что мы сегодня делаем с PIM и так далее. То есть это мультикаст, который, собственно, работает.
Спасибо.
Я еще чуть дополню, особенно насчет централизованных контроллеров или распределенного. Централизованная функция вовсе не обязательно значит, что она представлена каким-то одним-двумя элементами. Это может быть централизованная функция с очень распределенной реализацией и, собственно, очень много контролирующих элементов в облачных системах примерно так и выглядит. И да, распространенные популярные решения — это как раз иметь состояние по умолчанию, в котором у нас может не оптимальный форвардинг, но хотя бы есть connectivity, а контроллер улучшает эту ситуацию. Ну, я наблюдал некоторые такие применения. Вот. И встречный вопрос маленький по поводу RSVP-TE, проблемы которого, ну, его давно эксплуатируют, проблемы известны и довольно плохая масштабируемость, и даже некоторое количество открываемых у вендоров багов на тему «у нас через эту коробку прошло больше такого количества туннелей, и все стало совсем плохо». Насколько много и часто туннелей, на которых зарезервировано больше нуля, вы наблюдали? И чтобы это был не автобэндвидth.
То есть, в принципе, замена достаточно логичная и была востребована большей частью людей, которые пользуются RSVP.
У меня коротенький вопрос по поводу SR over EP. Он сейчас где-то как-то реализован, то есть это все софтверованный пока? Или
он реализован на Juniper и на Nokia, я не знаю насчет Cisco.
В железе.
В железе. А про бир, я надеюсь, в Тбилиси.
Ну, да. А, кстати, поднимите руки, пожалуйста, кто знает, что такое бир. Я думаю, у нас есть пара минут на то, чтобы Джефф
Если кого-то интересует,
сказал,
то
что это, и дальше было понятно, куда смотреть. А дальше мы перейдем уже к перерыву на кофе и сможем продолжить обсуждение в фойе.
Значит, бир — это новая технология, которую мы построили где-то, начали 3 года назад. BIR — это акроним для Bit Index Replication. То есть что происходит? Мы, когда пакет создается, создаем bit-mask, в которой, значит, encoded наши receivers. То есть когда мы посылаем ее и следующий девайс получает, он знает, кто receivers этого стрима, он изменит bit-mask и опять-таки пошлет его. То есть это, в принципе, достаточно просто. Вся эта информация опять-таки распределяется через ISS или SPF. То есть, в принципе, это нормальная технология, в отличие от PIMA, где обе ноги были сломаны.
Ну что же.
И опять-таки, это достаточно популярно. На сегодняшний день мы видим большой интерес из Азии и банков. То есть они пользуются этими технологиями сильно. И то есть имплементация в этом году появится от всех больших вендоров.